So today we are going to start with new chapter, current electricity. So what is an electric current? Let's start with the definition of an electric current. So electric current is defined as the electric charge, amount of electric charge flowing through some region per unit time. Okay. Current we denote by letter I. I is equal to charge Q which is flowing through some region divided by time. Okay, so this is definition of current. Now this current through a conductor is not always constant. Okay, it keeps on changing. So if we consider this wire, suppose, so amount of charge flowing through the cross sectional area of this wire, it is not constant. Okay, it keeps on changing, it fluctuates. So that's why we take very small interval of time, let's call it delta t. So current is defined as I is equal to charge which flows through this cross section. Let's suppose it is delta q in time delta t. Okay, so we take limit delta t tends to 0. Okay, so we know everything is made up of atoms and molecules. Metals are made up of atoms which have 3 electrons. So not 3 electrons, 1 2 3 electrons in their outermost shell, right? These metal atoms, they give up those electrons. Okay, at room temperature, those electrons, some of the electrons, they gain enough energy to come out of the outermost shell, outermost orbit, and they move freely inside the metal wire. So at room temperature, what this metal consists of is a positively charged ions mostly, and negatively charged free electrons. Okay, so these are negatively charged free electrons. So they move randomly in all possible directions inside the metal. Okay, so this negatively charged free electrons, they move in all possible directions, in random directions with different velocities. Okay, so okay, so in metals you have this collection of uh, large number of free electrons which are available for conduction, right? That's why metals are good conductor of electricity, and non-metals, or we can say the insulators, they are not. So now suppose we apply some external electric field. So suppose we apply some external electric field to this metal wire, what will happen? So let's suppose we connect positively charged surface on this side and a negatively charged surface on the other side. So electrons, they will start moving, right? They will start moving in this direction. So this negatively charged surface, let's suppose we connect two plates like this. We keep two plates, positively charged plate and a negatively charged plate. So what happens is electrons, they will start moving towards this positive plate. Okay, and if we consider any cross-sectional area, so some net charge will keep on moving, some net charge will move through the cross-sectional area. Okay, so some electrons will cross-sectional area at any given time, so some net charge moves. Okay, and due to that there is flow of current, we can say. So then there is a very important law which tells us the relation between the current flowing through a conductor and the potential difference that we apply across the conductor. Okay, so here we have connected a positive and negative plate. That means we have given some potential difference. Okay, this is a medium, we have applied some potential difference, right? So Because of that potential difference, there will be flow of current, and the law that tells us the relation between current and the potential difference, it is known as the Ohm's law. Okay. So what does the Ohm's law say? So at any given time, the potential difference that you apply across the ends of a conductor is directly proportional to current flowing through conductor. Or you can say current flowing through the conductor is directly proportional to the potential difference. Okay. Or you can say first power of potential difference. So there is no second power, third power, etc. etc. You have first power of both. V is directly proportional to I, or I is directly proportional to V. And the proportionality constant between these two is known as resistance. Right. So V is equal to R multiplied by I, where R is known as the resistance, and its meaning is clear from the name itself. So it is the opposition to the flow of these electrons, opposition to the flow of an electric current. Okay, the resistance R is directly proportional to the length, and it is inversely proportional to the area of cross section. Okay, the resistance is directly proportional to the length of the wire or any material that we have, and it's inversely proportional to area of cross section. Right. So now why is so? So for an example, if we consider a cylinder like this, suppose its length is L, area of cross section is A. So now suppose some current flows through it. Okay, some current flows through it. Okay. So now Ohm's law tells us that V is equal to R multiplied by I. Right. Ohm's law tells us the potential difference across the ends of this conductor is directly proportional to I. Okay. So now see, so there is some current flowing through this conductor, and when we apply some potential difference. So here in this case the potential difference is suppose V. Now what will happen if we consider conductor having twice the length? If we connect, let's suppose this conductor and an identical conductor. So suppose same current is flowing through this conductor also. What will be the potential difference across the ends of this conductor? It will be same, right? Potential difference across ends of this conductor is V. That potential difference across ends of this conductor should also be equal to V. Okay. Now if we join the two conductors, what will happen? So you will get a big conductor having same area of cross section, but whose length is 2 times. Okay, length is twice L. Now same current is flowing. I is the current flowing through this conductor. But now what about the potential difference? So potential difference across the ends of this conductor would be 2 times V. Okay, because uh, potential difference for this much length is V. So if you increase the length, then potential difference will also increase, just like the case of capacitor. Okay, in what happens in capacitor? Potential difference between two plates of a capacitor is equal to what? It is equal to, so V is equal to E times D, where E is the electric field, right? E is the electric field. So if electric field is constant, then if you increase the separation between the two plates, what will happen? Potential difference is directly proportional to the separation, right? If D is made twice, what will happen? Potential difference will become twice. So just like that, in this case, as you make length twice, what will happen? The potential difference will become twice, two times. So what happens to the resistance then? R dash will be equal to, you can say it is V dash divided by I, because V is equal to R into I, R is equal to V upon I. Okay, so which is 2 times V upon I, you can say, and that's equal to 2 times of R. Okay, if resistance of this conductor is R, resistance of this conductor will be 2 times R. Next thing is, how is resistance inversely proportional to the area of cross section? Okay, so remember, resistance is what? It is opposition to the flow of charges. Okay, so suppose we consider the cylinder and we apply some potential difference. So I will just draw plus and minus. Okay, we apply some potential difference to the ends of this cylinder. Now what happens? Current will flow through it. Okay, electrons will flow through it. So now if I break this cylinder into two pieces, okay, I cut it half, I cut it like this, such that the area of cross section becomes half and half. Okay, so this wire I will cut along the diameter of this circle, you can say. So now if Q is the charge flowing through this conductor, what will be the charge flowing through upper and lower region? If you consider area equal to A by 2 and A by 2, so charge flowing through this one, okay, this area is A by 2. So charge flowing would be what? Q by 2 from this section, right? And Q by 2 from this section. If you cut it like this, okay? So it means what? That if you decrease the area to half, potential difference is same. The potential difference here is same. Okay, between these two ends, the potential difference is same. But you have decreased the area to half, so current flowing becomes half, because charge flowing through this part, this region, becomes half. Okay, so that means current is directly proportional to the area of cross section, because if you reduce the area of cross section, current will reduce. Okay, so therefore now, okay, if area is, let's say, A dash is equal to A by 2, so I dash, current flowing through upper part or lower part, you can say, will be equal to what? I by 2. Okay, and we know V is equal to R multiplied by I. Okay, V is equal to R multiplied by I, that is R is equal to V upon I. But V is the potential difference across ends of this conductor, the complete conductor, okay, whose resistance is R and current flowing through it is I, right? And we want to find out the resistance of a conductor having half of the area of cross section. So R dash will be equal to what? V divided by I dash. Okay, and that is equal to, you can say, V divided by I divided by 2, and that 2 will go to the numerator. So it is 2 times of V upon I, or you can say it is 2 times of R. So area becomes half, area of cross section becomes half, resistance becomes 2 times, twice. That means resistance is inversely proportional to area of cross section. So this is simple to understand. So now it's clear that resistance is directly proportional to length. It's inversely proportional to area of cross section. So we can say, therefore, resistance of a wire R can be written as some constant which is written as rho multiplied by length upon area. Okay, it is some constant rho multiplied by length upon area, right? And this rho is now property of a material. Okay, rho is property of material and it is known as specific resistance of a material, or it is also called as resistivity. It is also known as resistivity. So it is different for different materials and it depends upon some intrinsic factors. Okay, so it is different for different materials. We'll see the equation for this and expression for specific resistance. Okay, so it's because of specific resistance is different for different materials, the resistance of different materials would be different. Even if the two materials, let's suppose we have two wires made up of two different materials, they have same length, same area of cross section. So since the resistivity is different, the resistance would be different. If I consider this expression for the resistance, it is rho multiplied by length divided by area. Then Ohm's law can be written as V is equal to, V is equal to R multiplied by I. So it is equal to R is rho multiplied by length upon area multiplied by I. Okay. So then you can take L on the other side. Okay, length of the material on other side. So if you consider a wire like this, so when you apply some potential difference, that means what you are doing is you are applying some electric field, right? So if electric field is constant, then you can say the potential difference is equal to what? Electric field multiplied by this length. Okay, and if you take length on the other side, so I can write this as V upon L is equal to rho multiplied by I upon A. Okay, so what is V upon L? Potential difference divided by length. So you can say it is potential gradient, right? That is the electric field. Okay, so this is electric field. Okay, where electric field E is equal to V upon L, and we have current density. Okay, we define current density J as I upon A. Okay, so denoted by capital J or small j. So if we put V upon L equals to E and I upon A equals to J, we get relation between current density and the electric field. Okay, what's that relation? So the electric field E is equal to rho multiplied by J. Okay, so electric field is equal to rho multiplied by J. Or if you want current density, then current density J is written as 1 upon rho multiplied by the electric field. Okay, and 1 upon rho, the reciprocal of resistivity, is known as conductivity. Okay, so here we define conductivity, equal to 1 upon resistivity, and we use this symbol sigma to express conductivity. Okay, so it gives us J is equal to sigma times E. Okay, the relation between the current density and the electric field This J is equal to sigma times E. Okay, this is another expression for Ohm's law, we can say, right? So because see, we started with Ohm's law, we just substituted R is equal to rho multiplied by L upon A. Okay, so this is another expression for the Ohm's law. Now there are too many relations and we need to memorize all of them. Okay, so next what we are going to do is we are going to derive the Ohm's law, okay, from basics. We know that there will be electrons inside this conductor and metal ions, and atoms. Okay, so these are suppose positively charged metal ions, and we have negatively charged electrons which are moving in all possible directions with all possible velocities. In absence of the external electric field, what will be the average velocity of these electrons? It will be zero, right? Because electrons are moving in random directions. Okay, so we can say the number of electrons that are moving in this direction and number of electrons that are moving in exactly opposite direction, it would be same, right? There is no bias. Okay, so we can say that in absence of external electric field, average velocity of electrons would be zero. Average velocity of electrons is zero. Okay, so let's suppose u is the average velocity. So how can we write u? So it will be u bar. This is three-dimensional, right? U bar is equal to, suppose there are n number of electrons, so it is sum of, okay, v1 plus v2. Let's take u1 u2. Okay, so u1 plus u2 plus so on and so forth up to plus un bar divided by n, where n is number of electrons, right? We can write this expression as summation of ui's from 1 to n divided by n, and this will be equal to what? 0 in absence of an external electric field. So now what happens when we apply the external electric field? External electric field will accelerate these electrons. Okay, so electrons will get accelerated from negative terminal to the positive terminal of external electric field, right? They will move like this. Okay, so suppose external electric field is applied. So when external electric field is applied, what will happen? There is acceleration. Okay, acceleration of electrons would be what? We know force is equal to mass multiplied by acceleration, right? Newton's second law. And how much is force acting on an electron due to the external electric field? So force is equal to charge, which is minus E multiplied by the electric field. Okay, so let's consider vector expression. So it is minus of E multiplied by E bar, capital E bar. It's equal to m times A, and therefore we can say that A bar is equal to minus of E multiplied by capital E divided by m, where m is mass of the electron and minus E is the charge on the electron, right? So this would be acceleration. So now these electrons, they are moving inside the conductor. So they will collide with the atoms inside the conductor, the ions inside conductor and the other electrons. Okay. And what will happen after the collision? So suppose an electron was moving in some direction. Suppose this electron was moving in this direction. Then it collides with this ion. So its direction of movement, it will change. Okay. So initially, suppose it had some velocity. Now its velocity will change completely, right? So now what will happen? So suppose an electron gets some velocity. Let's call it u only. After the collision, electron starts moving with some velocity after the collision, and time since the last collision is suppose t, okay, for an electron. So how much would be its velocity now? We can say, suppose that for ith electron, for, okay, we are numbering electrons. So ith electron, ui is its velocity just after the last collision. Ui is its velocity just after the last collision, and ti is the time since last collision. Okay. So what will be its velocity now? So its velocity can be written as what? Vi bar. So V is equal to u plus at, right? U bar, ui bar plus a multiplied by this time ti. Okay, but what is a? Sorry, it's a bar. It is same for all electrons. Okay, acceleration of all electrons will be same. So a bar is equal to minus of E times capital E bar divided by m. So let's put that here. So what do we get? So Vi bar is equal to, okay, we get ui bar plus, actually it will be minus of, okay, E times E bar upon m multiplied by ti. Okay, so this is for one electron number I. Now if we want to find out the average velocity, what will happen? So let's find out. Therefore the average velocity of electrons after we apply an external electric field. So after external electric field is applied, so it will be summation of Vi, I goes from 1 to n, divided by number of electrons, right? So it is equal to, on right hand side also we'll do the same thing, summation of ui, where I goes from 1 to n and we have divided by n, okay, or let me do it separately. So minus summation of, so this E times E bar upon m I can take out actually, because it's a constant. So I have summation of I goes from 1 to n of Ti divided by n. Okay, so we know about this thing. Okay, what is this? This is zero, right? Average velocity before the external electric field was applied, right? These are random velocities with which electrons are moving inside the conductor. Okay, so if you sum up all the random velocities and divide by number of electrons, you will get average velocity, okay, before any external electric field was applied. So this term is zero, right? This term is zero. And what do we have here? So here it is E times E bar upon m, which is a constant, multiplied by, you have time since last collision for electron number 1, electron number 2, electron number 3, so on and so forth up to electron number n. If you add all those times and divide by n, what do you get? You get average time since last collision for all the electrons. Okay, and for conductor, this term will be fairly constant. Okay, and it is known as, it is denoted by tau. Okay, so this term will be 0, this term will be 0, this is V average of all electrons, so it is 0 minus E multiplied by E bar upon m into tau, okay, where tau is known as the average time since last collision of all electrons, or you can say it is average time between two collisions of an electron. Okay, so it is also called as relaxation time. So electron is colliding and then it gets some time to relax. Okay, it is also known as relaxation time. Okay, so V average equal to minus E times E bar upon m multiplied by this relaxation time. So see what we have got. So this average velocity of electrons, it doesn't depend on time. Okay, we might think that when we apply electric field, what will happen? Electrons will get accelerated. Okay, electrons will get accelerated, and as so for more time we keep that electric field, more will be the average velocity of electrons. But that thing doesn't happen. Okay, average velocity of electrons is constant, and this is known as the drift velocity. Okay, this velocity is known as drift velocity. Okay, what is drift velocity? It is average velocity of electrons in an external electric field. Electrons of a conductor, or you can say material, in presence of external electric field. Okay, in presence of external electric field. So it is denoted by Vd, and it's equal to Vd bar, d for drift. It is equal to what? Minus of E times E bar upon m multiplied by tau. So here we can see that this drift velocity is directly proportional to E bar, the external electric field. Okay, and the proportionality constant, we can say Vd is directly proportional to E, and the proportionality constant between Vd and E. Now I am just considering the magnitude. Okay, just magnitude, not the direction. So the proportionality constant between Vd and E is denoted by mu, and it is known as mobility of electrons inside a material. Okay, so where mu is known as mobility of electrons in material. Okay, and you can see mobility is denoted, it is defined by E times m multiplied by tau. Okay, that's E upon m, charge divided by mass multiplied by tau. What is tau? It is average difference. It is average duration between two consecutive collisions. If average uh, if average duration between two consecutive collisions is more, then mobility would be more. What does it mean? That the drift velocity would be more. Okay, so this is a property of a material, right? Density of material is more. What will happen? Then there are more chances of collision. Okay, temperature is more. If temperature is more, then atoms are also, they are wiggling, so then also there are more chances of collision. Okay, so mobility depends on what? It depends on the material. It is property of a material, right? It is different for different materials. Okay, though the same thing is moving, what is moving? Only electrons are moving. If we talk about conductors, then electrons are moving. Still, the drift velocity of electrons would be different. Okay, and we'll see that current depends on drift velocity. So current will be different for the same electric field, or you can say for same potential difference. Okay, so this is what gives rise to resistance. Okay. Once again, let's consider our cylindrical conductor. So if we consider a cross-sectional area inside this conductor, now we can say electrons have gained some average velocity, right? So on an average, some electrons will drift. They will get drifted towards this positive terminal. Okay. So electric field is from positive to negative. Electrons are moving from negative to positive, right? Electrons are moving from negative to positive. So how is charge moving? So we can say negative charge is moving from negative to positive terminal, because electrons will be, they will get repelled by the negative terminal, they will get attracted by the positive terminal. So negative charge is moving from negative to positive. But historically, we define current as positive charge moving per unit area through some area per unit time. Okay, positive charge moving through some area per unit time. So current is taken, the direction of current is taken as opposite to the direction of electrons. Okay, so if negative charge is moving from, let's suppose, right to left, we can say equally that positive charge is moving from left to right. How? Because if some negative charge moves from this portion, let's suppose this portion to this portion, it crosses this region, what will happen? So for an example, suppose there is plus q charge here. Okay, charge is equal to q and q, right? And suppose some charge minus delta q, okay, minus delta q moves from this region to this region, what will happen? So what happens is charge on this region will be q, it will be q plus minus delta q, okay, and charge on this region will be what? It will be q minus delta q, because charge minus delta q has moved from this region to this region. Okay, so you can see that Q minus delta Q will be the charge in this region. Q plus delta Q is charge on the other side. So you will get same result, same result. If you consider, so this in this what we have imagined is the negative charge is moving from this side to this side. You will get the same result if you imagine some positive charge is moving from this side to this side. Okay, so suppose positive charge is moving from left to right. Okay, so Q, now Q dash will be equal to what? Q minus delta Q, because charge on this region will decrease, and that positive charge plus delta Q, it will move on the other side. Okay, so charge on other side will be equal to what? So let's suppose this is Q dash left, this is Q dash right. So it will be Q plus delta Q, because this region will gain some positive charge. Okay, so this is equivalent. The definition of current is equivalent. Negative charge is moving from right to left. It means that positive charge is moving, okay, from left to right. So now once again let's consider this conductor, and suppose in some sorry. So now once again let's consider this conductor, and now suppose in some time delta t, the charge moves from here to here. Okay, so charge over here moves from here to here. This much is the distance. Let's call it L. Okay, so let's name those surfaces. Let's call them A1 and A2. So I can say in time delta t, charge at A1 moves to A2, right? So actually electrons will move from A2 to A1, and we can say positive charge is moving from A1 to A2. So how much would be the current? Okay, so suppose delta Q is, suppose the charge moved. So how much would be delta Q? Can I say it will be number of electrons per unit volume multiplied by this much volume? Okay, because see, if that means if you consider area over here, which is at same distance from this area, the charges from this area, they will get shifted. Okay, they will get shifted to this area. They will move through this much distance, because charges from here, they are moving through this much distance, right? So since charges at A1, they are moving through this much distance, and average velocity of charges is constant, so we can consider an area at the same distance, okay, from A1 on the left side. So charges from there will move till A1 in the same time, because average velocity is constant. Okay, so we can say the charges have moved through this much volume, right? Charges have moved through this much volume, or we can say charges have moved through volume from A1 to A2, volume between A1 and A2. Okay, so delta Q will be number of electrons per unit volume multiplied by volume between A1 and A2, right? So number of electrons per unit volume will denote by n, small n. This is density of electrons, multiplied by volume between A1 and A2. It is, now let's suppose this area A1 and A2 is equal to A. A1 is equal to A2 is equal to A. area of cross section is it is same, okay, but we are just naming those areas. We are just naming those regions A1 and A2. Okay, so how much would be volume? So this area multiplied by this length, right? So it is n times area multiplied by length. This is charge moved. And how much would be the length? So length is equal to, so we can say velocity is equal to distance covered divided by time taken, right? Velocity is equal to distance covered divided by time taken. And what velocity would be this? This is the drift velocity. Okay, it is the average velocity of electrons inside the material. So Vd is equal to distance covered upon time taken. Sorry, time was delta t. So L is equal to, we can say Vd multiplied by delta t. Okay, so you get delta Q is equal to n times A multiplied by L, sorry, Vd multiplied by delta t. Okay, so then you can take this delta t on, I missed one thing. Charge moved will be equal to what? Number of electrons per unit volume multiplied by charge on one electron. Right? It is just number of electrons. There is no charge. Okay. So I can say this is charge on electron multiplied by number of electrons per unit volume multiplied by volume between A1 and A2. What is charge on an electron? Charge on an electron is equal to E. Okay, we'll consider its magnitude only because we are considering positive charge which is moving from A1 to A2. Right, so it will be E times N into A into Vd multiplied by T or delta T. Let's take delta T on other side. So what do we get? This implies that delta Q divided by delta T is equal to N times E multiplied by A multiplied by Vd. Okay, and what is delta Q upon delta T? This is current. So current through conductor, which is delta Q upon delta T. I is equal to NEA times Vd. Okay, so there will be lot of expressions and we have to memorize, unfortunately, all of them. All right, so this is current flowing through conductor. It is equal to N, which is number of electrons per unit volume, multiplied by E multiplied by A, which is area of the conductor, multiplied by Vd. Okay, what is Vd? Vd is the drift velocity. What is an expression for drift velocity? It is minus of E times E upon m multiplied by tau. So I will put this over here. So what do I get? I get I equals to NEA multiplied by, I'm just taking the magnitude of drift velocity. It is E times E upon m into tau. That is, you get NE square tau upon m multiplied by A multiplied by E. This is your I. Okay. Then I can write E. Okay, I can, all right, I will just derive one thing from here. So I will take A on the other side. Let's name this expression. So I will call this expression something. Let's call it 1. Okay. So I can say I upon A is equal to NE square tau upon m multiplied by E. And what is I upon A? I upon A is the current density, right? Current per unit area. It is current density. So what is current density? It is Ne square tau upon m multiplied by E. So remember our previous expression for current density. So here I can say J is equal to what? Ne square tau upon m multiplied by E. So comparing with J is equal to sigma times E. What do we get? So we get that sigma is equal to Ne square tau upon m, right? Sigma is equal to Ne square tau upon m. Got it? Yes, no? Then this is sigma. So what is sigma? It's conductivity. Then what is resistivity or what is conductivity? It is reciprocal of resistivity, 1 upon rho. So what will be resistivity? It's reciprocal of conductivity, right? Therefore, I can say resistivity of a material rho is equal to m divided by Ne square tau. This is expression for the resistivity of a material. Okay. After that, so let's name them 1, 2, 3. Okay. Right. Then let's consider expression number 1 again. Okay, expression number 1 again. So what do we get? So actually we have derived the Ohm's law. Okay. So J is equal to some constant. See, N is a constant for a material, number of electrons per unit volume. E is a constant, mass of electron is a constant, and tau, the time between two successive collisions. This is average time. So it is also a constant for a material, right? So this is another form of Ohm's law. J is equal to what? Sigma times E. So we have derived that. Okay. But if we want to derive Ohm's law as Ohm stated it, what do we have to do? We just have to substitute E is equal to what? V upon L, right? E is equal to V upon L into this expression number 1. So I can say I is equal to what? So this is from 1, I is equal to Ne square tau upon m a e, Ne square tau upon m a e. And what is E? So we know that E is equal to V divided by L, potential difference divided by length. Let's substitute that. So if we substitute that, we get Ne square tau upon m, or we have called it what? The conductivity. I'm sorry. Or I can write this as 1 upon resistivity. Right. We have, okay, defined it. The conductivity is Ne square tau upon m. Resistivity is reciprocal of that. So this is 1 upon resistivity. Multiplied by, we have A times E, and what is E? It is V upon L. Now let's move the things on left hand side. So we get V is equal to rho multiplied by L upon A multiplied by I, and what is this thing? This is resistance. Okay, this is resistance of a material. So we get V is equal to R multiplied by I, right? So we have derived the Ohm's law as Ohm stated it. V is equal to R multiplied by I. Got it? So this is Ohm's law, and Ohm's law considers that resistance of a material is a constant quantity. Okay. So Ohm's law has some limitations. What are limitations of Ohm's law? So let's see limitations of Ohm's law. So first limitation is that Ohm's law predicts that resistance of all materials would be constant. So if a material has to obey the Ohm's law, it must have constant value of resistance. But it is not so for all materials. Okay. So therefore, different materials, they show different kind of curve. So what will be curve between V and I? So if you take Ohm's law, I is directly proportional to V or V is directly proportional to I. Okay. So if we plot current versus resistance, what should we get? We get line like this passing through origin. Okay. Because no potential difference means no current. Okay. So this is V versus I, or we can take I versus V. No potential difference is zero across a conductor, then current would be zero. Okay. So if we take slope of this line, here actually if we plot V versus I and take slope of the line, then we'll get V upon I, and it is resistance. But we'll see various materials. Okay, for an example, a semiconductor or a semiconductor diode, etc. For them, the curve is not like this. Okay, this curve is not like this. Okay, it is slightly different. Okay, so that means the resistance is not constant. Okay, so Ohm's law considers that resistance is constant, but resistance of all materials is not equal at all values of potential difference. Okay, all values of V. So it also depends on the potential difference. Now you might say, why should it depend on potential difference? Because as you increase the potential difference, what will happen? The velocity of electrons will increase. Okay. So now we have considered the static case. What is static case? That the atoms inside conductor, they are steady, and on an average the number of collisions will be constant, right? And okay, while deriving this Ohm's law, what we have considered is sigma, which is conductivity. It's a constant. See, sigma depends on what? So three things defining sigma: N, E and M. It is fairly constant, we can say, right? So if you take some volume of the conductor and there are n electrons inside that volume, so electrons are not moving outside the conductor, they are not going anywhere. So number of electrons per unit volume is a constant. E is a constant, M is constant. But what about tau? What is tau? It is average time between two successive collisions. So as you increase the voltage, the potential difference, what will happen? Velocities of electrons will increase, and that means average time between the collisions will decrease. Okay, so this graph, okay, since the average time between collisions will decrease, okay, because there will be more frequent collisions because velocity is more. Okay, so since tau decreases, that means conductivity decreases, and rho is reciprocal of conductivity. So if conductivity decreases, rho goes up. Okay, rho increases, resistivity increases. That means resistance increases, right? So the graph between V and I will not be like this. So most of the materials will show, so it will be fairly constant for up to some potential, and then it will start to deviate the graph will start to deviate like this, okay, towards the voltage axis. So this is the expected curve, ideal curve we can say, which is a straight line, and this is real curve for most of the materials. Okay, so the resistance doesn't remain constant at all values of V. This is first thing. Then let's consider second point. So resistance also depends on temperature. Okay, resistance of different materials would be different at different temperatures. Resistance of a material, generally for metals, the resistance will increase as you increase the temperature. Okay, so that means the resistance is not constant. So for different temperatures, you will get what? Different current for the same potential difference applied, right? So this is another thing. And for semiconductors, what happens if you increase the temperature? The resistance will decrease initially, and then it starts to increase. Okay, so we can say for semiconductors, okay, for semiconductors, resistance initially starts to decrease. Okay, I can say decreases as V, not V, temperature increases. This will happen first, and then there will come a point when it will start to increase again. Okay, so semiconductors show some weird pattern for current. Okay, and then it is not applicable to all the components that we use in electric circuits. For an example, diodes, semiconductor diodes don't obey Ohm's law. So now let's come back here and let's see the resistivity. Okay, so what will happen? Okay, we have discussed that as you increase the temperature, what happens? The resistance of conductors decreases. Sorry, as you increase the temperature, what happens? Resistance of conductors increases. Okay, so we have discussed this, that as temperature increases, the resistivity of conductors increases. Why so? So m is a constant, n is a constant, E is a constant, tau will change, right? So as temperature increases, what will happen? Tau will decrease. There will be more frequent collisions. Okay, and as tau decreases, rho goes up. So this happens for metals. This happens for metals. Okay, then if we talk about semiconductors, what will happen for semiconductors? So for semiconductors, or let's take this expression here. Let's discuss what happens to the resistivity of metals and semiconductors versus temperature. Okay, so we have this expression, rho is equal to m divided by n e square tau. So for metals, as temperature increases, as T goes up, we can say time between two successive collisions will decrease because velocities of electrons will increase okay, and atoms, they will also start to wiggle, right? And therefore there will be more frequent collisions. So tau decreases, and therefore resistivity of metals will increase, okay. Then for semiconductors, what will happen? So their resistivity decreases as temperature increases first, okay. So the resistivity decreases as temperature increases, the resistivity decreases. Why so? It's because, see, now we have seen the tau will decrease, average time between collisions will decrease, there will be more collisions if temperature increases, right? It is true for metals, it is true for semiconductors also. So tau will decrease, but now the number of charge carriers, okay, in case of semiconductors they are electrons and holes, which we will discuss in semiconductors chapter. But even if you consider electrons, what will happen? So initially semiconductors have 4 electrons in their outermost orbit, okay. So they don't want to lose electrons, right? And so for them, uh, losing electrons and gaining electrons, it's equal thing, okay. So they don't want to lose electrons also, they don't want to gain electrons also, so they believe in sharing, right? So okay, if you have less than 4 electrons, you will lose them to become stable. If you have more than 4 electrons, you will try to gain more electrons, because you need 8 electrons to be stable in outermost orbit, okay. But semiconductors have 4, for them gaining electrons and losing electrons, it is identical case, okay. So they share electrons, all right. So now as temperature increases, in case of semiconductors at room temperature, there are not many free charge carriers, meaning there are not many electrons available for conduction. As you increase the temperature, what will happen? Electrons will gain some energy, okay, sufficient energy to come out of outermost shell. So there will be more number of electrons available for conduction, okay, more number of electrons, and we'll discuss that in semiconductors, more number of holes also, okay. So for semiconductors, number of charge carriers, charge carriers meaning holes and electrons, okay, increases as temperature increases, because more number of electrons will become free, and therefore what will happen now? So if n increases, okay, and tau decreases, so it is competition between n and tau, it is competition between n and tau, right? So n increases faster compared to decrementing tau, and that's why rho will decrease, because you have rho is inversely proportional to n, right? It is inversely proportional to n and tau both. So tau decreases, rho will increase. If n increases, rho will decrease, but n decreases faster compared to incrementing tau, compared to decrementing tau, okay, and therefore rho decreases, right? So this happens initially as you increase the temperature. Now let's suppose you keep on increasing it, okay, you make it very high. So at some limit, the number of charge carriers that can be free, that can be available for conduction, it will approach, there will be a limit for that also, okay. Semiconductor cannot lose more than 4 electrons, so it will lose 4 electrons, right? So it has made 4 electrons free for conduction. So what will happen now? Okay, all electrons are roaming around. So now, if you increase the temperature, what will happen? So time between collisions for available electrons will decrease and cannot increase anymore. So at some limit, n will be a constant and tau decreases. Okay, tau decreases. So then what will happen? The resistivity will start to increase because it's inversely proportional to tau. This decreases, resistivity will increase, right? So is it clear? This is the dependence of resistivity of metals and semiconductors versus temperature.